much for inviting me. I would like to know who is in the audience. So, are there only people who does gravity or not? Are there people who does not work in gravity?
We all know gravity.
Okay, good. And does everybody do modified gravity or not? Not everyone. But okay, then I have some slides which are for some general audience, and some slides which are more for people who works in modified gravity. So if it will be too easy what I will talk about, tell me that. So I will present you today the theory of modified gravity, which we call the torsion by gravity. And
again, I'm sorry.
Center,
Yeah.
enter. Does not work neither.
Should be with the arrows. Okay, something interesting is going on. I'm sorry.
Yeah, so first I will tell you what this theory is based on.
This one.
So I should enter.
Well, I normally use the arrow. This one.
This works
Okay.
now. So the two main components of this theory is metric and independent connection. It is considered independent variables, and the only the only way these two variables are linked is the condition of the metric compatibility, and usually it is much more convenient to work with Hilbert formalism, because in this case the condition of the metric compatibility is algebraic. And the first theory which considered non-zero torsion, as you know, was Einstein-Cartan theory, which is equivalent in vacuum to GR, and torsion is not independent in this theory, does not propagate. And then the following question arises: whether we can create some theory where torsion will obtain the dynamics, will become a dynamical degree of freedom. And to build such a theory, we will do the following. We will take a Lagrangian of general relativity. We will add to it the Lagrangian of Einstein-Cartan theory, and we will add some nonlinear terms. The simplest is to add some quadratic terms. Now let's add some free parameters, and this is our torsion by gravity Lagrange. A bit of non-relevant for the today talk information is that all these actually started from considering a bit more general theory of dynamical torsion, where we were motivated by explaining the self-acceleration of the universe without cosmological constant, and we thought that we succeeded, but then I found some very hard instabilities, so we did not think about it anymore, and then we concentrated on more minimal theory, which is torsion by gravity. So on my torsion by gravity 3, I have 2 fruits. One of them is massless, spin 2, and another one is massive spin 2, and this is why it is called torsion by gravity. Because as if in biometric, because as in biometric gravity, we also have here 2 massive spin 2 particles, a massless spin 2 and massive spin 2. Yes. And massive spin 2 is generated by torsion, actually, because this R, is a curvature made using torsion-full connection, and when we make such a structure, we obtain a field which describes a massive spin 2 field. Okay, some explicit field equations. The field equations are second order in both connection metric. And as you can see immediately here, the source, the only direct source of torsion is a quantum spin density, and we will come back to it a bit later. So the first question which everybody asks is about ghosts, right? Whether theory has ghosts or not. And it is quite complicated to check that we don't have ghosts on a general background. I don't know yet how to do it. It looks very complicated, but still some progress was made. We proved the absence of ghosts in some particular cases, which you can see here. Yes, here I wrote a comparison between biometric gravity and torsion by gravity it is very useful to compare these two theories because they have something in common, and even in some cases there is a formal limit between a formal link between torsion by gravity and biometric gravity. I will tell you later. Yes, and it is one of my future directions of study is to prove the absence of ghosts. So after the theoretical consistency being discussed, we can start to explore the universe, which this theory describes. It's like you open a door in another universe, and you can discover it step by step, and you can compare it to what we know about our universe, and we can then think, is it similar or not? So which basic objects are in our universe, like stars, black holes, and planets, for example. So let's start from objects like planets, or from something which is described by Newtonian limits. And the gravitational potential looks like this. So we have a usual term and a cover term. Yes, I'm sorry about that. You don't see my Lagrangian anymore. I could write it somewhere, but I don't see exactly where. Maybe I will show it to you again. Just to remind, we have 3 parameters, eta, kappa, and this guy also, which does not participate in anything symmetric. So for now, we don't take it into account. And so kappa is the mass of the massive spin 2, while the parameter eta measures the relative strongness of the interaction of the massive spin 2 interaction.
So this, sorry.
Yeah.
So this kappa was the kappa in the third term.
Yes. Normally, when I give a talk, I write it somewhere, but now
well, you can write it down on the blackboard if you want. If you put it up to you.
No one will see. Okay. Yeah. Yes. Yes, and since there are some observational restrictions for you cover type interaction, we immediately obtain a quite strong restriction on the parameter eta. So the eta is small, and we do not consider very small masses of the massive spin 2. We do not consider, for example, cosmological type masses of the massive spin 2, and I will explain you later why it happens. Then stars. What happens with stars? We numerically simulated stars, and the most exciting thing is that actually torsion is generated by not only by a spin, but also by simple simunu, like any matter, where we generate torsion, which was interesting to discover. Actually, we can see it even here already. That torsion is generated by neural matter. And another very interesting thing is that, so here you can see the metric of the star, the torsion of the star for some parameter eta, which is not very small. If eta becomes small, then this curve will go down, will go closer and closer to the GR metric. But the torsion will stay further one, even if we send eta to 0. I don't actually understand how it happens.
Sorry. So you're sending kappa.
Eta is
You said eta to 0.
yes.
And kappa is arbitrary.
Yes, kappa is arbitrary.
And this is Newtonian or a Newtonian analysis, or is it the full theory?
It's a full theory, yes. So it's an interesting phenomena. So we generate big torsion. And speaking about big torsion, yes, so we generated, but we cannot really feel it because only quantum spin feels it, and actually, yes, only quantum spin feels it because the torsion connection enters the Dirac equation. But even so, the torsion enters Dirac equation by in such a construction, and curiously, in the torsion by gravity, this thing equals to 0 in many cases, like in spherical symmetry, for example, or in the Newtonian limit. So it's not easy to directly detect torsion, which makes this theory more viable in a sense. Apparently, it's not that easy to kill.
Actually, sorry, can you go 2 slides back?
Yes.
No, okay, that's fine.
Yeah.
So what exactly, so then when you explain again, what are you doing when you make eta go to 0? What is happening? So you say that eta goes to 0, are those lines with the different solutions?
When eta goes to 0, then matrix
Goes to GR.
yes, but torsion, which is here. So this here I
When you say torsion, what exactly do you mean? Tensor the
I mean some components of torsion in a spherically symmetric static situations where we have only 2 non-zero components of torsion, and they are here. Yeah. Yes. Another interesting feature is related to Vainshtein mechanism. Everybody knows what is Vainshtein mechanism or not. No, okay. So it's such an interesting thing. For example, in massive gravity, the perturbation expansion, which is valid, far away, it stops being valid at some distance before the matter source. It is not valid anymore, and instead of that, there exists another series expansion, which looks very differently, and which gives different observable predictions, which in a sense helps to agree theory with an experiment, because in massive gravity, the perturbation theory, which is valid outside, gives predictions which are not in agreement with observations, and such a phenomena, it cures this problem. But in torsion by gravity, the perturbation theory does not is not breaking down, and is valid everywhere. So we don't need any Vainstein mechanism. And it is very unusual, and what is interesting? Yes.
Here you have two scalar mode, two vector, one scalar, two vector, and two vector mode, like by ordinary by gravity. But
I
so how many
don't have
degrees is here?
scalar modes. I don't have vector modes. I have.
No, you don't have it. You don't have a bigravity modes. So that way you have a physical five. In fact, in our sector, you have our next sector, you have bigravity is here. I don't know. But my question is how to get. They will figure out and later you are going to get the surface of scalar mode, the vector mode in the radiation solar system. Or
Don't understand your question. Sorry.
hello, I'm just asking. In the mass gravity, for example, I don't know. If you in the Hassan so the diagram for a type of by so mass gravity five bigger.
Yeah.
Yeah, but you have the same number.
Yes. Yes, exactly. Yes.
In your case, there's no excitation of the scalar mode, the vector mode, around maybe around the sun or.
I see. So I think if I understand correctly, this question is when you build these solutions, which of these 5 degrees of freedom is in the solution? You see what I see? Is it a scalar mode? Is it a vector mode? That's the question, right? Is it scalar time?
I don't remember what does it mean in your language, scalar.
Well, I mean, you have
Vector.
5 degrees of freedom. I guess you have 1 or 2 scalars, 2 vectors, or 2 vector time modes.
I thought that I have one tensor mode, which corresponds to massive spin 2, and I don't understand how to decompose it into scalar and vector.
Usually, you can reduce these scalar and vector.
Then this
So maybe that-
language is not. I don't know this language.
How do you count the degrees of freedom?
Yes, it's a good question. So if the dynamics of my configuration is described, for example, by 1 second order equation or 2 first order differential equations, then I say that I have 1 degree of freedom because I need the 2 initial data to solve my equations. This is how I count them.
I think about it.
20 minutes left.
I see. Okay. Yes, and another future direction of my study is to understand what does it mean in a quantum level, because this Vainshtein effect, which is classical, is related to the strong coupling which happens on a quantum level, and I'm very curious about what does the absence of the Vainshtein radius mean from the point of view of the strong coupling? Okay, now we finally go to the black holes. So yes, in heavy to gravity, black holes of Einstein type, I mean the same black holes as in jar, and also some hairy black holes too. In torsion by gravity, we also have all the black holes which are solutions of solutions in GR are also our solutions, and we also prove the theorem that it's impossible to add small hair to our Schwarzschild black holes, but also in the limit of very light massive spin tool. For example, when a massive spin tool is of cosmological scale, which is very light, there exists another type of black holes which is different from Einstein's ones. They are hairy and asymptotically flat. Yes, I'm speaking about only about asymptotically flat black holes, which means that far away you still have our flat space-time. But actually, we cannot consider in 5 minutes. I will explain why we cannot consider very light masses of them as if spin 2. So we, I will maybe not talk about this, but one question: did you compare how to say? Did you try to look what will happen from the point of view of gravity collaboration if the black holes in the universe are hairy?
I think Ariana so I have a student that's doing that.
Ah, it's interesting. I would like to look at it. Okay. And so let's concentrate on Schwarzschild black holes. Let us assume that the black holes that we have in our universe are Schwarzschild. But actually, the fact that they are Schwarzschild does not mean much, because still it can be an absolutely different objects with absolutely different properties. Maybe we will touch it and it will disappear. So how to understand the properties of a black hole in some theory of gravity? What the easiest thing that we should do if you have a black hole here?
Stay away from it.
No, it's yes, you're right. But then you will not know anything. So what should we do? What should we do with this black hole? Yes, we should kick it. Yes. Because when we kick it, we immediately can understand many things. And the first important thing we can understand is the stability, because maybe we kick it a little bit and then it either disappears completely, either is transformed to something else. For example, in biometric gravity, it was found that Schwarzschild also black holes are unstable if the mass of the mass 6.2 is small enough. And the idea was that there is a transformation from Einstein black hole to a hairy black hole, which was also found in biometric gravity. But then apparently recently it was found that well, yes, in some cases this hairy black hole is stable. In this case, it's fine. We pick the Einstein black holes transforms itself to hairy, and we're happy. But is in some for some part of the parametric space, the hairy black holes are also unstable. Then it's a problem. So what we found is that our Schwarzschild black holes are stable. Another thing that we found is that you know, when we write equations which describe small perturbations around black holes, we found that there is a point where these equations become singular, absolutely singular, and I don't know how to explain it. It looks not good at all, and the only way to avoid this singularity is to put it inside the horizon of the black hole, because this way you don't see it, you don't have problems. And yes, to avoid this singularity in the equations, we should satisfy this inequality where kappa is a mass of the mass 6.2, it is almost zero. And this is an horizon of a black hole which you consider, and you should consider all the black holes that you know or you think exist in this world. And well, I think we can for sure say that for now we have no evidences about existence of black holes with a mass smaller than 2 solar masses. So I put here four solar masses, and I obtained that we should not consider masses of the massive spin-2 which are smaller than 10 to the minus 10 electron volt, or in other words, it means that the how to say the area, the distance of the modification of gravity is around 10 kilometers or smaller. Yes.
Could you say a bit more about the singularity? What exactly is going on? So I guess you had the second order differential equation.
Yes.
And then for kappa smaller, then this something happened. But what exactly happened?
For kappa equals to this,
yeah,
then I think the right hand side of the equation goes to infinity. Yes. And yes, if you put this singular point inside the horizon, then it's fine. Well, fine. In some sense. Maybe it's still, yeah. It might mean something. And yes, I have some ideas what it might mean, but
There it's not like coordinate singularity.
no, no, unfortunately no. Yeah.
So in the differential equation, you set the torsion to 0, but it's not implied by 0, right? So
Sorry, what?
In the differential equation,
Yeah.
you had like CR plus something, right? Depending on torsion. And in the differential equation, for finding this, you set the torsion part to 0. But that is not implied by the equation, right? You could have found like more general solutions for the differential equation.
I did not understand again.
No, I think is that true? I think the document if it was kappa should not be there. So I think the question is, when you're looking for these solutions, are you setting the torsion to 0?
No, no.
So I mean, I think they are spherically symmetric, but they must have torsion.
Wait. Schwarzschild black hole is Schwarzschild black hole completely, in the sense that torsion is 0. Yes, torsion is zero, and the metric coincides with the GR black hole metric of Schwarzschild metric. I mean.
Yeah, but in the background it is, but when you fluctuate it, okay, sure. Yeah. That's like that. Yeah.
Yes. Yeah.
The plot that you showed of the metric. So when you went to GR, so the metric went to the GR metric, but the torsion did not go to out. The torsion was
Yeah, I think that was for a star. So
Yeah, it was for star. I don't think that these two phenomena are connected. at least not directly. Yes, and I just wanted to say that maybe this can be cured by some higher order completion of the theory, just an idea.
I think there's other theories with this problem, like one Intel type, where you have singularities as well, even in static. And therefore, you need to go to this.
Yeah. Let me see what I have. I have several slides with some technical details. Should I tell them or not? It depends
So
on your taste.
in terms of time, I mean, you have like 5-7 more minutes. If that's okay.
5, 7. I mean, okay. So let me skip them, and then I can tell them later or in private discussion. Just let me tell also a few words about superradiant instabilities in torsion high gravity. Everybody knows what does it mean, superradiant instabilities, right? No? Okay, yeah. So it's superradiant is when you have a spinning black hole. Then if you have a massive particle, it might happen that a massive particle comes and takes some angular momentum of black hole. And then spinning black hole spins slower. And superradiant instability is when you have a spinning black hole, and then you just add some small perturbation, and then scalar particles appear, and they are like bound in some area around black hole, and they are like this, but the black hole, it loses its angular momentum, and it's not a spinning black hole anymore. So in this very interesting work, particularly, and in other papers too, what people do, they compare this time of development of such instability with some other characteristic time. For example, we were observing Cygnus X1 for 10 or 20 years, and we know that all this time it is spinning with the same angular momentum, more or less. And then it means that if some superradiant instabilities take place, their characteristic time is very, very long. and this allows to put some constraints on the mass of the massive massive particle, because all this happens when you have a massive particle in the theory, and in particular from massive spin 2 particles, this region was excluded, but since we already have such a limit coming from this singularity appeared in black hole perturbations, then at least for now, super radiant instabilities does not touch us, because this limit does not give anything new. Yes.
But is it there? So when you return a current matter in the torsion bigravity, does it have instability?
You know, it's too complicated to study. It is much simpler to say that even if it has, it will not give any new limit in comparison with the limits which already is here.
Well, but not necessarily, because if you have terms, the field equations are different. So it might be that in regions that in standard massive gravity would be timescales above the Salpeter timescale, in your theory, they could be lower. So you could have new machines. I mean, I like the argument, but it's not.
Yeah.
It's only valid.
Yeah. Of course, it is not a rigorous proof. Yes, and the last thing I just wanted to say is that another reason to kick black holes, if you have an opportunity, is that how to say, yes, when you when the LIGO, Virgo, and all the coming also see a gravitational wave signal, it looks
Were you
Yeah, we
looking
need to
for?
go throughout the.
yes. Yeah. Yeah. Now it looks something like this, and this part is how to say, this part is described by kicking. So it is very interesting to study what happens in black hole, because then you can compare it with observations, and this is what I'm going to do soon, but I did not do yet. And this is the main things I wanted to tell you about the torsion bigravity worlds. And if anybody wants to know more technical details, please ask. I'm ready to answer.
Thanks very much. So I'm sorry, it was also my mistake. We said that a bit late, so it's already time. But if you don't mind staying 1 or 2 more minutes, we have time for 1 or 2 more questions.
has the problem of the point particles studied this theory, like there are particles moving the physics that comes from the conservation of energy momentum, right? I mean, that's what I would think. Like
maybe if you can take off your mask, yes.
Yes, sorry. Has the problem of the point particles has it been studied in this theory? You know, like sort of the concentration or stuff like that, or even without spin, like there are particles moving the physics, right?
Yes.
The physics of the background.
Here too. Also, it follows.
It doesn't happen here.
Huh?
It doesn't happen here.
Yes, here also particles follow geodesics if they have no spin. So actually, we should say that macroscopic bodies follow geodesics, while when we have a quantum spin, we might have some effects from torsion because torsion interacts with spin still. In this theory, in many cases, this interaction is zero by accident, but still in some cases it will manifest itself. Yeah.
Any other questions?
Yes, I see.
Yes.
Do you know how your theory compares to quantum gauge theories?
Which theory?
The quantum gauge theories, because have been studied by the
What do you mean by saying quantum gauge?
Like that are built, so there is only one key term for the turbine normally, not for the connection. This theory. And you have a kinetic term for the connection.
Yeah, I think I understood your question. Concurrent gauge theories. I think I don't remember, but they are very similar. I forgot. Maybe it is even speaking about the same, but in other words. And your question concerning kinetic term for connection, you want to know how torsion or connection becomes dynamical. This is what you want to know.
Usually in the quantum gauge series that they study, it's quite general.
Yes.
So basically they have your first term and the product terms.
Yes.
But the ones in the middle, they don't consider it. So I wanted to know what is changing.
Instead of that, they write some terms which are quadratic in torsion. I can write this Lagrangian in this way. I can then it will have this term plus some quadratic terms in torsion, and this term will not exist. Yeah, it's just more a bit more beautiful way to writing this Lagrangian, but that's all.
So probably
It's the same.
You have your answer, then check if there is stability or not. Because there is quite a formal paper
Who did it? Who did this paper?
So there was the first one, from what I know, I
don't know, 2001, I think, on Esther and you. And lately there was another one, the dated one from
You will show me, but
and
I've
what I
doubts.
found in this theory, just for a comment, is that linearly they are normally unitary on a Minkowski and on a symmetric background. You can find unitary theories that are linearly unitary and also correspond to the normal level of things like this. But when you go to the nonlinear theory, you have basically all these Poisson constrained variables that changes and you generate more degrees of freedom, like strong equivalence. How it works in
This looks a little bit
yeah,
too good to be true. You will show me this paper, okay?
Yeah, so maybe if you don't mind, you can continue because it's getting late. So thanks very much everyone for coming. So let's thank our speaker again.
If you enjoyed the video, like and subscribe.